Hi, everyone. Welcome to the final week of the MTV Nuclear Engineering Summer School. I think I've met some of you before when I did the Monte Carlo week lecture. So if I didn't see you there, I am Shaun Clarke. I am the Associate Director of the MTV. And today I'm going to be co-presenting this lecture on radioxenon detection with Tessa Maurer, who's a student in our group as well. So hi, Tessa. So I'll be doing the first half of the lecture, and Tessa will pick up kind of roughly halfway in between. If you have any questions, please feel free to put them in the chat, and we'll do our best to collect them and answer them at the end. So with that, Tessa's going to drive the slides here, and we can get started. So this is a brief outline of the topic of the lecture today. We're going to be, again, talking about radioxenon detection, and there's some bullet points here of the content that we're going to go through, but the main takeaway here that we want you all to gather from today's lecture is what is radioxenon monitoring and why is it important? So there's some acronyms here, CTBT, IMS. I'm going to go through a lot of the history and the background, and then Tessa's going to take over kind of in the second half and talk more about the detection systems that we're developing in our group here at the University of Michigan. So slide, please. First, a bit of history. The chart at the right is a rather complicated chart that shows the history of nuclear weapons testing. And you can see you see this middle line here, kind of middle horizontal axis. Some bars extend above the axis, some bars extend below the axis. And what this is showing are the number of nuclear weapons tests, and the bars that are extending upward from that middle axis are above ground tests, and the bars that are extending below that axis starting in 1962 or so are underground tests. So it just kind of shows you, and the length of the bar is the number of tests, and it's kind of color-coded by country. So what this chart is meant to show is just a history of nuclear weapons testing, and you can see several features in this chart that are marking key points in history along this process, and they're listed here in the bullets on the right. And that little blip I mentioned in 1963, where the tests go from predominantly above ground to predominantly below ground, corresponds to the implementation of the Partial Test Ban Treaty, which banned nuclear weapons testing, or rather limited it to only underground. Following that, in 1968 was the onset of the Non-Proliferation Treaty, which essentially was an agreement signed between the nuclear powers and non-nuclear powers that was trying to ensure that nuclear weapons technology was not proliferated for nefarious purposes. And I think we had a lecture on that earlier this semester. So a few other things kind of went on throughout history, and eventually you come to the main outcome here, which is what leads us to our discussion today, is the Comprehensive Nuclear Test Ban Treaty in 1996. And you can see once that happened, there were very few tests following the implementation of this Comprehensive Nuclear Test Ban Treaty. After that, there's only a few tests, mostly by North Korea and a couple by Pakistan that you can see there in the late 90s. This chart is from the ctbto.org website, so you can go and find a lot more details there if you're interested. Next slide, please. So what is the Comprehensive Nuclear Test Ban Treaty, or the CTBT? In short, it prohibits all nuclear explosions everywhere around the world. That's the long and short of it. The complex part about it is, while it is a treaty, it is not actually entered into force. So it's been signed by several countries, but not yet ratified. So the US is one of the states, you can see them listed here in the third sub-bullet there, is one of the states that have signed the treaty, but not yet ratified. So the treaty itself is not completely enforced due to this status, but what it did, the outcome of the CTBT, was this verification regime that has been established in order to verify that treaty once it does, if it ever does, come into full force. So this verification regime is comprehensive in nature and takes care of on-site inspections, as well as monitoring for any nuclear explosions that may occur around the globe. Slide, please. The monitoring framework for the CTBT is known as the IMS, or International Monitoring System. So what this system is, and you can see it, the picture on the map there at the right, is a set of 337 facilities around the world that are set up to continuously monitor for nuclear explosions. And this IMS framework consists of 4 technologies: seismic detection, hydroacoustic, infrasound, and the 4th, radionuclide, which is going to be the topic of our conversation today. The first 3, seismic, hydroacoustic, and infrasound technologies, are sufficient to detect any explosion or earthquake around the globe. The radionuclide monitoring is the key that will attribute these detected explosions as being nuclear in nature. So that's the first main point here, is the radionuclide monitoring is the only component of the IMS framework that can attribute an explosion as being uniquely nuclear in nature. When we say radionuclide detection, what do we mean? We mean the detection of radiation and noble gases in the atmosphere, and these samples are collected in the atmosphere, and they're sent around the world to one of 16 laboratories where they're then processed, and we can do some isotopic identification from there. Slide, please. So these stations detect radioactive particles from noble gases, and the chief of these is xenon. And the reason, I think I have another slide on this later, but xenon is produced during nuclear explosions, and even if the explosion is underground, because xenon is a noble gas, it can escape from these underground cavities and training areas into the atmosphere, where it can then be detected. There's atmospheric samples that are collected 24/7, and again, they're then shipped off to labs for processing to then collect or identify the concentration of the various xenon isotopes in these continuously collected air samples. The pictures on the right are just some photographs of what these stations look like in their various placements around the world. Slide, please. Just a bit of background about radionuclides on Earth, and kind of these are kind of our background terms, if you want to think of it that way. When we're looking for xenon in the atmosphere or other radioactive elements in the atmospheric samples, there are some other sources of radiation that can interfere with that signal. So the top 3 bullets there are listing naturally occurring sources of radiation, things like potassium-40 and thorium and uranium decay series products are found in nature, mostly in soil. And also there's things from the cosmic rays like carbon-14, sodium-22, things like that. These types of radionuclides are existing mostly in soil samples. The cosmic rays kind of are coming down as well, but they don't often interfere with atmospheric sampling that we're doing when we're talking about radioxenon. The bottom 2 bullets, however, can interfere with radioxenon monitoring. And the two main sources of background or man-made background that interfere with radionuclide monitoring are medical isotope production facilities and nuclear power plants. Both of these facilities can emit radioactive emissions, and those can be collected in our atmospheric IMS samples that can then interfere with our ability to detect radioxenon in those samples. And we'll talk later about kind of how we can mitigate this background in some ways. Slide, please. Okay, so xenon. Why radioxenon? What is xenon? Xenon is a noble gas, which means it's inert. Okay, if you remember your high school chemistry, noble gases are inert, meaning they don't react with materials around them. So what that means in practice is there's a very high probability that the xenon gas will diffuse up through the ground and escape the underground containment following an underground nuclear test. So the fact that it's a noble gas is the first reason why xenon is important. The second reason why xenon is important is it is a very high probability fission product. So I think Fission Week was last week, where we talked about nuclear fission and all of its detail. But for the sake of this discussion, what's important is when fission occurs, that high Z nucleus, whether it's U-35 or plutonium or what have you, that high Z nucleus splits into two pieces, and there's a very high chance that one of those two pieces will be xenon. That's what we mean when we say the second bullet here has the highest cumulative fission yield of any noble gas produced. So the xenon is produced from fission with very high probability. That's the second reason why we like to monitor xenon for these nuclear tests. Radioxenon, when we say radioxenon, we mean the radioactive isotopes of xenon. Radioxenon consists of 4 primary radioactive isotopes, and you can see them listed here on the slide and also in the table, along with their half-lives. So when we say radioxenon, we mean 131M, 133, 133M, and 135. The M in the number there means metastable. So these are metastable states with short half-lives on the order of days. So all of these isotopes get produced in fission, and they all some of them decay to one another, and it's a kind of a messy decay chain. And then we can use the signatures from these decays to detect each of these individual isotopes, and the quantity or the ratios by which these 4 isotopes get produced can tell us something about the mechanism that produced them. Okay, whether it was from a nuclear reactor, a nuclear explosion, so on and so forth. So it's important in radioxenon monitoring for whatever system that you're using, that system be sensitive to all 4 of these isotopes of radioxenon. Slide, please. This chart shows in practice one of the ways that we detect these radioxenon isotopes. It's a little bit complicated, but if we start on the right, you can see the table. And in short, these 4 radioxenon isotopes decay through mechanisms that emit correlated photons and electrons. Okay, sometimes that photon is an X-ray, sometimes the photon is a gamma ray, sometimes that electron is a conversion electron, sometimes it's a beta. But in short, these isotopes decay by correlated electron and photon emission. So we use the fact that these decays produce correlated particles to separate them from the background with very high specificity. So the table at the right shows the energies of all those major decay products. And then the chart on the left, the colorful heat map there, shows what it looks like if you detect these various isotopes and project them in a histogram of gamma energy versus beta energy. And you can see that when you project the data in this way, there are several nice and obvious bands that start to pop up. So the top one there labeled xenon 135, that long band in the green box there is the continuum produced by the detection of this 900 keV beta, 905 keV beta from xenon 135. The band at the bottom is the band from xenon 133, and if you look really closely in the boxes that are labeled 131M, 133M, you can see little peaks in there, and that's from the conversion electrons that are monoenergetic. So when the conversion electrons get detected, it's a single energy in the spectrum. So when we project the data in this way and define these regions of interest, you can see the green box, the blue boxes, the red box. If you take all the counts integrated in these various regions and then plot the ratios, you can get a result like what's shown in the middle. Okay, so plotting here is the ratio of 135 to 133 versus the ratio of 133M to 131M. And when these data are plotted in this way, the samples from nuclear power plants nicely separate themselves from the samples from nuclear explosions. So you can see the 2 regions on that plot in the middle. That line, the diagonal line toward the right of the plot, is just meant to show the discrimination of these 2 regions. So it's important that we have a system that has sufficient energy resolution and detection efficiency to be able to separate out these regions of interest and produce count rates from all 4 isotopes individually, so that we can then create these ratios, make these plots, and discriminate so-called benign events from nuclear power versus what may have been a nuclear explosion. Slide, please. So the top part there is what I was kind of just talking about, isotopic ratios and background levels. This is really important regionally. So depending on where the radioxenon monitoring station is located, that region of the globe is going to have different backgrounds than say some other regions. So characterizing the local background level is very important. So for example, if this station were in the proximity to isotope production facilities or reactors, it's going to have a different local background than a station that was, far isolated from such facilities. The systems also have an automated gas processing system, which essentially is what's used to kind of extract the xenon from the overall air sample. And these systems are designed to have a minimum detectable concentration of 1 millibecquerel per cubic meter for xenon-133. Those units are a little bit esoteric, but suffice to say that's a really, really small amount. So these systems are quite sensitive. It literally is needle in a haystack sort of problem. You're looking for very small amounts of xenon in very large samples of air. So there are systems that exist. These systems have been around for decades now, and a lot of the technology is aging, and there are areas where these systems can be improved, and that's what we're going to be talking to you a little bit about for the rest of the lecture. But basically what we're looking for here with these systems is you always want higher sensitivity and better efficiency, right? And the way to do that, there's a couple ways you can do that. One is energy resolution. So if we can define those regions of interest I showed on the previous page, if we can define those, smaller and in a more precise way, that'll help us get higher precision estimates of the count rates of the various isotopes. And the other way is by reducing what's called the memory effect. So these detectors are constantly acquiring data, and they flush the samples in, take a measurement, empty the detectors out. And what can happen in some materials is the xenon that you're measuring can actually diffuse into the detector itself and get stuck in there, basically. And what happens in that case is the background for any subsequent measurement is then elevated. Okay, so if we can investigate new materials that don't exhibit this memory effect at all, or at least have a reduced memory effect, that can also improve the overall sensitivity of these detection systems. Slide, please. This is a little bit about the gas system and how the samples are processed. So essentially, it's a high level charcoal filter that just the air samples are pushed through to get rid of any particulates or any other contaminants, and kind of purify the sample before it's placed into the actual detector. And then the sample is counted, and then the International Data Center is the name of the entity that collects and houses all of these data from the various samples and the various stations around the world. Slide, please. Okay, so now we're going to talk a little bit about the detectors. So one system, so there's references on most of these slides. So if you're interested in any of this content, you'll be able to look up these papers. But I want to just give you a high level view of what exists on these last couple slides, and then Tessa will begin to take over about the systems that we're developing. So one system is focused on high purity germanium. So high purity germanium is kind of the gold standard for gamma ray spectroscopy. It has excellent energy resolution on the order of tenths of a percent at cesium energies. So what this allows the system to do is define these regions of interest very accurately, and thereby producing very precise count rates for the various isotopes. The downside is these systems need to be cooled, continuously cooled. So high purity germanium does not work at room temperature. It needs to be cooled to liquid nitrogen temperatures in order to work. So that causes a couple problems. One, because these systems are kind of continuously monitoring data, there's a large burden there in terms of the actual cooling, and it also means the systems are quite complex. Okay, so you either need a large mechanical cooling system, which requires power and can break and all the things that come along with that, or you need a system to circulate liquid nitrogen around the detectors to make sure they remain cool. So it's complex. It also is quite expensive. These germanium detectors themselves are several tens of thousands of dollars each. So when you talk about deploying these all around the globe with these hundreds of stations, the cost becomes prohibitive very quickly. But if cost is not an issue and complexity is not an issue for cooling them, germanium is indeed the gold standard for gamma ray spectroscopy. Slide, please. The other option that folks have been investigating over the past several years are silicon-based detectors. Silicon-based detectors also have excellent resolution. The downside of silicon is the efficiency. So these are kind of very thin silicon wafers that are sandwiched around a gas cell. And we say gas cell, we mean the little piece of the detector that holds the actual air sample. And these planar silicons are surrounding the gas cell, and there's a sodium iodide around the outside, which is a good system. Again, it's excellent resolution. The issue is the efficiency. So there's very low efficiency for the silicon wafers, but there's no memory effect. So again, memory effect, as I mentioned before, is this property where the xenon diffuses into the detector material, which is more common for organic detectors. So things like plastic scintillator, which I'll talk about later. Those kind of organic detectors have a much higher propensity to absorb the xenon sample than something like silicon. So no memory effect is good, low efficiency is bad. So this system has been under development for a while now as a possible replacement for the systems that are existing in the field, which are plastic sodium iodide cells that we'll talk about later, but has not yet been fully adapted just due to its low efficiency. Next slide, please. Lastly, and probably the most experimental of these detectors are things called phosphorus detectors, or even CZT. So CZT, or cadmium zinc telluride, is a semiconductor detector that operates at room temperature. So it has excellent gamma ray spectroscopy capabilities, almost as good as high-purity germanium in the sense of energy resolution, but it operates at room temperature. So CZT has good potential in this area for those reasons. The problem with CZT is it's also kind of expensive. So most of the CZT detectors that are existing are on the order of a centimeter or so. So they're still quite small. So efficiency can be an issue, but definitely a promising material. I know there's been some work trying to design a system loosely based on the silicon system I showed on the previous page, but with CZT instead of silicon. And that system has shown some promise as well, because the CZT, while they're small, they're bigger than silicon. So there is an efficiency improvement there. At the bottom here, it's a concept called the phosphorus detector, which basically means sandwiching together multiple different scintillators. So kind of like what you see on the right there, the far bottom right of the slide, you see a BGO, cesium iodide, plastic. You basically nest all these different scintillators together and use complex correlation logic to have very high specificity to the background. The issue here is because you're combining all these different scintillators, the energy resolution is going to suffer because there's just so many different scintillators, and all of those scintillators get coupled to the same light readout device. So I don't believe this system has shown too much promise yet for actual implementation in the field, but certainly from a physics standpoint, it's a very interesting concept. Slide, please. So this slide shows the beta gamma coincidence system, which is essentially the systems that are currently deployed in the field. So I'm going to let Tessa take over now and tell you about these systems and the ways that we are researching them at the University of Michigan. So Tessa?
Thank you, Dr. Clarke. As you said, my name's Tessa. Hello, everybody. I'm a student here at the University of Michigan. And so I'll be talking about this last type and then some of the work that we've been doing at our lab with a possible alternative for this radioxenon monitoring. So this is a beta gamma coincidence detector. So these are what's most commonly employed in the field right now. And so Dr. Clarke walked through some other types of detectors and how they could apply to radioxenon monitoring, but this one is what's typically used in the field, actually. And so some more information about how they work. So they operate at room temperature. So he mentioned the HPGE detectors, and a big con of those is that they require such extensive cooling and continuous cooling. These don't. You can operate them at room temperature, which makes them ideal for field use. And so how these work is that there's a beta or electron cell, and then a photon detector or a gamma cell. And they work in coincidence with each other. And so if you kind of look at that picture that I have here, this is a coincidence detector with these rounded plastic cells. And in that case, that's like the electron detector. And that acts as like the sample container. And so with these two cells or detectors working with each other, we get background reduction from coincidence measurements. And we also get near 4 pi geometry for really high efficiency measurements. And so what's typically used for the beta and gamma cells, so for the plastics or for the electron detector or beta cell, we usually use plastic scintillators. And that's what's shown in the diagram there. The rounded plastic cell, you can see that that's kind of the container of the detector, and that's what's serving as the beta cell. For the gamma cell, we usually use inorganic scintillators, typically sodium iodide. And so this is just an idea of what typically is used. And next, I'm going to get into some of the challenges that radioxenon monitoring have. And so we've already touched on a few of them briefly and brought up some images that we've talked about. But just to revisit that, we need to be able to very confidently distinguish between different isotopes. And so the 4 radioisotopes specifically for xenon. And so this figure is shown here up on the top right, just as a recall. And we need to be able to accurately like quantify and distinguish between these, because we need to be able to distinguish a medical isotope facility leak from a nuclear power or a nuclear weapons detonation. So we can use the ratios of these different radioisotopes and plot them on this graph as pictured on the bottom right here. And then depending on what region it falls into, it'll be determined what the source of that increased xenon level is. Is it from a nuclear power plant leak? Is it from a medical isotope production facility? Or is it from a nuclear test that someone is trying to hide? And so that's very relevant. And it's really important to have high energy resolution and high resolution in general for our detectors, so that we can very accurately, again, quantify and distinguish these different isotopes in order to determine what event is actually occurring. And so typically we use the coincidence detectors with plastic and sodium iodide cells, and we use that at room temperature, which again is really good for field operations. But we do run into some problems with plastic scintillators. So as I mentioned, we need to have very good resolution, but plastic scintillators don't exhibit the best energy resolution. So it can be a little bit difficult to identify these different isotopes. And additionally, if the plastic scintillators don't have the proper coatings, we can see something called memory effect, which Dr. Clarke talked about a bit. And so in these plastic scintillators, if we see memory effect, or just, the basically retaining of radioxenon samples in the actual scintillator itself, that will increase the minimum detectable concentration. And so we want to keep that really low. If you remember the number that Dr. Clarke quoted earlier in the presentation, it was about 1 millibecquerel per cubic meter. And so if we raise that too high, what we run into is false negatives. And so it'll be really difficult to distinguish if a particular event is, or it'll be hard to distinguish the raised background level as a nuclear explosion event and so forth. So it's important to reduce memory effect and have high energy resolution. So those are some of our main challenges for radioxenon detection. And so we can look into different alternatives to the currently used plastic cells in the beta gamma coincidence detector system. So we don't have to use a plastic scintillator as a beta cell. We can use something else that has, better energy resolution and reduced memory effect. So one of the things we've looked at is organic still beam scintillators as an alternative. And so our previous work had shown that we have improved energy resolution. So this decreases those ROI bounds that on like the image I showed before, which leads to increased sensitivity. Additionally, still beam has pulse shape discrimination capabilities. This means that we can discriminate radon alphas from xenon betas. And also, I'll get a little bit more into this in the next slide, but we have decreased memory effect with still beam when compared to plastic scintillators. So of course, this improves the detector sensitivity and extends our measurement time. So a little bit more into our work in studying memory effect with the still beam versus plastic. So we did this work a while ago. The reference is here on the slide, comparing plastic and still beam detectors, specifically the memory effect that they exhibit in the presence or after measuring xenon-133. And so we had very similar setups. We just had plastic for one and still beam for the other. And we measured this xenon-133 sample and then evacuated that sample. And so memory effect, again, is when even after evacuating a sample of radioxenon, some of it diffuses into the scintillator and remains. And so these figures show exactly that, especially the one on the right. So after some time has passed after evacuation, you can see the plastic scintillator still exhibits or still has radioxenon present in it. And so it's still popping up showing that radioxenon is present, and specifically 4.5% of the sample was remaining in the plastic, which is pretty significant and will affect that minimal detectable concentration and could lead to things like false negatives and so forth. And in comparison, if you look at the still beam on the right, we see much reduced memory effect. It's actually 100 times smaller. So this was really encouraging, and still beam has better energy resolution, reduced memory effect. So it looked like it could be a really good alternative to plastic scintillators, but still beams are very expensive and they're not easy to shape. And so that gets into my next slides here. So still beams, you have to physically grow those crystals. So to have it in any geometry you want, like you could a plastic easily, is a little bit more tricky than you might think. And so we've been looking at even a different alternative to the plastic scintillators, and this is organic glass scintillators. This is a new material from Sandia National Laboratories. It's newly developed, and we are currently in the first stage of this project. We are evaluating and characterizing the glass to see if it would be a potential substitute of plastic scintillators in the beta cell for beta gamma coincidence detectors. So unlike still beam, these can be melt cast into pretty much any shape you want. And so that's a major pro over the still beam detectors. So we want to verify that these have good characteristics, have better resolution and things like that than the plastic cells. And then ultimately we want to be able to look at the memory effect of this material. And so this is a little bit more background on what the actual OGS material is made up of. As I said before, this is pretty new. This is from Sandia National Labs. And so it's emitting in the blue energy or blue light spectrum. And you can see an example of a pulse from our actual OGS scintillator here on the top. And so this is what a typical pulse looks like that we see from the scintillator. And the material is mainly made up of this compound C42H36 silicon. In reality, the chemistry of this material is a little bit more in depth than I'm probably qualified to go into, but I've put a reference here on the slide. If anyone is interested, I definitely suggest going to that. there's some more things like a wavelength shifter added, and different polymers that's added to this glass to make it ideal for the applications that we're interested in. And so this reference details all that information pretty well if you're interested in looking into that. And so we get the raw material from Sandia National Laboratories, but everything else we do in-house. So we get the glass in these little vials, and they're basically just little shards. And we melt the material with a heat gun and a hot plate at 200 degrees Celsius, and we connect it to a rough vacuum to remove any dissolved air. And I've got a video here to show that process. At this point, the glass is already melted, and we have our heat gun here, and we're tapping it against the copper plate. And if you can see, it's there's those bubbles rising up to the top. And so that's the gas removal process. And so what's not pictured is it's connected to a vacuum. And the vacuum is, of course, aiding in removing that dissolved air. So once the glass has been degassed, we pour the melted OGS material into custom silicon molds and then set it in an oven for over 14 hours so that it can gradually return to room temperature. And again, this gets into some of the big benefits of this material. Any kind of silicon mold we can make is whatever geometry we can make our scintillator, because we can just pour the molten material into that silicon mold and set it. So it really is advantageous over an alternative like still beam in that respect. Some other things we've been investigating are reflective wrappings used on our OGS so if you look at this top left picture here, this is a 3mm slab that's OGS, and we have diffuse wrapped it. So really what we mean by that is there's a diffuse optical reflective wrapping, Teflon tape in this case, that we wrap around all sides except this bottom piece, which is of course coupled to our PMT. So we won't wrap that, but by wrapping the rest of it in a reflective wrapping, what we're doing is we're theoretically redirecting escaped light back into the system, which will increase light collection. So throughout our characterization, we were also looking into things that would just improve the glass. And so we investigated reflective wrappings as well. The image below this shows some 6mm cubes that are bare. They don't have any wrapping. This is just to give you more ideas of what the material looks like. And so these are some of our preliminary results into our characterization of the OGS. And so specifically, this is comparing OGS and still beam. And this slide is focused on energy resolution. And so that's really important when we're talking about distinguishing between, different isotopes or different radioisotopes for xenon. And so what we did here was we tested OGS and then still beam, keeping as much as we could apples to apples. So instead of just going into the literature and finding, quoted values for the still beam energy resolution, we really wanted to make everything as much as we could the same. So same dimensions, same PMTs, things like that, so that the only variable we were switching was the material itself for the scintillator. And so we could definitively point a better energy resolution to the actual material itself. Say, the OGS is what's making this energy resolution better, or vice versa. And so what's studied here was 6 by 6 by 6mm cubed OGS and still beam cubes. And we tested them with both diffuse optical reflective wrapping and specular optical reflective wrapping. And we performed a cesium-137 Compton coincidence technique to determine the energy resolution. So not only did we use our cube of interest, but we used a sodium iodide detector, an inorganic scintillator, and placed a cesium source between them. And then from that coincidence technique, we were able to find the energy resolution. And so these spectra are shown here for the different configurations we tested, but the main takeaway is that in every case, the OGS cube outperformed the still beam counterparts. So that means that for the same geometry, the same dimensions, and the same wrapping, the OGS cube had a better energy resolution than the still beam did. And so you can see those energy resolution values listed in this table down here. And so we tested 4 different configurations. They were all 6 by 6 by 6 millimeter cubed OGS cube, or OGS and still beam cubes. And we tested different wrappings. And overall, the OGS specular wrapped cube performed the best. And so we also tested coincidence time resolution. And again, we were comparing between OGS and still beam, and then also investigating some things like wrappings. We also introduced some bigger cubes. So not only were we looking at 6 by 6 by 6 cubes, but also 12 by 12 by 12 millimeter cube specular cubed cubes. And so again, the main takeaway from this is that the OGS cube outperforms the still beam counterparts. And so we're seeing even higher resolution for the OGS than we are for the still beam. And this is really important because we've established through previous work and literature that the still beam is outperforming the plastic, right? So if we can show that the OGS is even better than the still beam when it comes to these different resolutions, that really puts the OGS in a good place when we're looking at talking about it as an alternative on the market to use for these radioxenon monitoring applications. And so a little bit of background on what this coincidence time resolution experiment entailed and how to read these diagrams here. So to do this, we had, every time we wanted to test a specific configuration, we had to do them in pairs. So say, for instance, we were looking at a 6 by 6 by 6 millimeter cubed diffuse wrapped OGS cube. So we'd have to take that cube and then another cube of the same material, dimensions, and wrapping, and then couple those two PMTs. And so we would place a sodium-22 source between those, equidistant. And in that way, we were able to get the coincidence time resolution. So say an event happened in the sodium-22 source, the time difference between the different detectors that were there, that's what we care about, and that was what has to do with our coincidence time resolution. So theoretically, or not theoretically, but ideally, we would have 0. The moment an event happens in the sodium-22 source, the detectors detect them at the exact same time. There's no time resolution, basically. But there really is, in reality, a slight difference between the timestamps between when a event is recorded in one detector and when its correlated event is detected in the other. And so that's exactly what's shown in these different plots. It's a histogram of the time difference between the correlated events across the 2 detectors. And the best performing configuration was the 12 by 12 by 12 millimeter cubed specular wrapped OGS cube. And again, as I mentioned, our OGS cube was outperforming the still beam counterpart. So, or at the very least, it's very similar. And so that was really encouraging. And because we both see not only energy resolution being better, but also coincidence time resolution. And so this really makes the OGS that much more interesting to investigate. And that we also have looked at OGS pulse shape discrimination capabilities. And so unlike the other 2 slides I was showing, those were focused with cubes. These looked at a slightly different geometry. These were rectangular slabs. And so I believe it was 12.7 millimeters by 25.4 millimeters. And the thicknesses of the slabs that we tested were 3, 4, and 5 millimeters thick. And we also tested only diffuse optical wrapping this time. We will in the future test other kinds of optical reflective wrappings. But we wanted to also look into the pulse shape discrimination capabilities of this OGS material. And so a little bit about what PSD means. If you look at this plot here on the left, this is a PSD plot. And so really what it is we're trying to distinguish between neutron and photon pulses. The cloud up here is from neutron pulses, and then the lower cloud is from photon pulses. And so the better separated these clouds are, the better the PSD capabilities, because the more confident we can be in saying, oh, that's from a photon, that's from a neutron. And so we have a quantity to that tells us how good a PSD capability of a certain system is. And that's called the figure of merit. And so the higher the figure of merit, the better our PSD capability. So we want a high figure of merit. And what we've done here is we've divided up every PSD into these gray lines you can see. They're kind of slanted. We just did different slices of our total integral. And then we found the figure of merit for each slice. Again, the figure of merit has to do with the PSD capabilities. And so in this way, we were able to compare across different configurations, the different PSD capabilities. These are all summarized in the far right plots. So if you look at the bottom right here, we have a californium-252 source. And we have the upper limit of the slice plotted, that's on the x-axis, and then the figure of merit for each of those slices on the y-axis. And we have all of our different tested configurations here. So in the solid lines represent the diffuse cases, so the diffuse wrapping, and then in the dashed lines represent the bare cases. So for the same color and marker, it's the same exact slab, just when it's a solid line, we had that additional diffuse wrapping. And so you can see that we have much better PSD capabilities when we introduce that wrapping, which kind of makes sense from what I mentioned before. It's redirecting any escaped light back into the system, which is just going to increase our performance. And we saw with the energy and time resolution that our reflective wrappings also were like the best performing cases. So that's all really encouraging. On the top plot here, this is just sort of a check, a sanity check here. And so this was all the different sources we used with a 3 millimeter diffuse wrapped case. So the same exact configuration, different sources. And what we want to see is we want to see it be nearly identical. So basically what that means is that the PSD capabilities should not depend on the actual source we use. And you can see that that's pretty much true. We used a californium-252 source and a PUBI source, and it's very hard to distinguish between the data series based off of the figure of merit. And so just kind of getting into more of the conclusions of this presentation. So radioxenon is really important because it's a very good indicator of nuclear weapon detonation. And specifically, if we're talking about underground nuclear weapon detonation, because of the noble gas and inert nature of radioxenon. And so right now it's achieved with continuous monitoring with beta gamma coincidence detectors. And that's a really important part of the verification regime outlined by the CTBT. And we do have a problem though with the beta cell specifically. The plastic scintillators that we usually use for the beta cell don't have very good resolution, and they have something called memory effect. And so we've looked into some possible alternatives. So still beam could be an alternative. It does not possess the same memory effect, and it also has better resolution, but that's really expensive and very difficult to shape. So we've been therefore investigating organic glass scintillators, which are easily shaped and have better resolution according to our preliminary results of compared to even still beam. And so this is really an exciting potential alternative to plastic scintillators in the beta cell for radioxenon monitoring. And with that, I'll open it up to any questions. I know we're getting close to time here, but thank you all for listening.
Great, thanks, Tessa. So we do have a few minutes for questions. I see 2 questions in the chat now. The first one is asking about, kind of generally speaking, about the suitability of organic glass scintillator in fusion reactors, which is certainly not my area of expertise. But I would just say, in short, this is a material that is simultaneously sensitive to both neutrons and gammas and detects both with fairly high efficiency. So I would imagine in these fusion applications, there are needs to detect neutrons and gamma rays in the back, from the background, from the reactor, to do things like, dose monitoring, things like that. So that's kind of my gut reaction about where this material could fit in that reaction space. But if you want to send me an email, maybe we could talk some more about that offline. The next question, if the organic simulator, glass simulator has a better resolution, can Stillbeam be completely replaced by OGS in all applications? Tessa, you want to take a stab at that one?
Well, this is a preliminary look, and so we're gonna complete a more comprehensive characterization of the glass in general. But yeah, so depending on your applications, maybe not. You might still want to be using Stillbeam, but it is, showing promising results as far as replacing it in for these Radioxenon applications. And so again, preliminary, exciting, and warrants further exploration, and that's what we're doing.
Mm-hmm. Yeah, that's great. The only thing I would add is the benefit, and Tessa mentioned this in the presentation as well, is just the way we can shape the organic glass into a variety of shapes. Stillbeam is a crystal, which means it has to be grown and then cut. So it's very difficult to make large sizes. So I think where I would see the OGS having an obvious advantage would be in applications where you need either a large or abnormal size or shape of detector. So I think performance-wise, it's similar, if not better. The Stillbeam, I will say, has better PSD, and I think Tessa kind of showed that, but we've shown that with other sizes of these materials in different shapes and sizes. So if PSD is your main concern, probably Stillbeam is still a better bet. Again, assuming you can get by with the limitations of size and shape. Other questions? Okay, I don't see any coming in. Just in case someone's typing, I will just remind you all that this is the final week of the summer school. We have 2 more lectures this week. Tomorrow is going to be Dr. Noura Bassumbul talking about medical applications. So if you're interested in radio isotope medicine, imaging, things like that, be sure to tune in tomorrow for Dr. Bassumbul's lecture. And then on Thursday, we're going to have Dr. Sierra Civils talking to us at a different time. So it's going to be 2 p.m. instead of the usual 1 p.m. And she is going to be giving an overview of research that's being performed at the Johns Hopkins laboratory. So we look forward to seeing you all for the final 2 lectures. And with that, I think we'll adjourn for today. Thank you all for your time and attention, and enjoy the rest of your day.